Well, welcome to our new seminar seasons, and it's my pleasure to introduce one of our own, Guoyin Shen, and as the first speaker of this season. And one thing is that I do want to encouraging everyone to look at the HP CAT and websites and look at the capabilities, and not everyone here really understand the capability of the HP cats and what they can do, what they can help you. And if I were a postdoc today, and I'm pretty sure I can come up lots of projects that I can do in the HP cat. And there are so many variety of techniques that can be used to address various questions. But today he's come here tell us one of his project with his associate and on the metastable melting. It's an interesting topic, but it's also showing some of the techniques used at HPCAT. And Guoyin and I actually share a very similar path, and he and I went to undergraduate together. And we end up working for Carnegie. And Guoyin got his PhD in Sweden was Saxena, which is also my advisor, and then came here for postdocs, and then moved on, and now he's the director for the HP CAT, and really it's a fantastic facility. I really want to encouraging all the people looking at the site. And here, it's all yours.
Thank you, Faye. And thank you for the opportunity to be here at the home institution and see many of the familiar faces and some of the new faces as well. So it's really nice. Faye mentioned about HPCAT facility, and several times when I was here at GL, I often talked about capabilities, facility, and techniques, this kind of development effort. Today, actually, I selected a topic about metastable melting. This subject, of course, is not new. It's ancient old. Recently, I have been interested in this topic mainly because of one pathway, that is through compression and decompression. And indeed, that through this work, I think that this metastable melting is probably more common than we thought when a pressure is applied. So I would start with the acknowledgement. Chen Ling, he was the postdoc. He was actually the main driver of this project. He did all the experiments and a lot of the research part of this subject. And then Jesse Smith, Stas Sinogagin, Yoshio Kono, and Changyong Park. They are all beamline scientists at HPCAT. And Curtis Kenny Benson, he's the beamline associate at HPCAT. And of course, the fundings are from DOE and NSA. I will start with the terms because when metastable is involved, it itself is rather, I should say, complicated and interesting. But the terms we use is also a little confusing. So I would like to clarify that what the terms that I use in this talk, at least. And also then the major part of my discussion will be mainly to provide experimental evidence of metastable melting under decompression. I will use bismuth and H₂O as examples. And then I will also try to discuss my understanding of this metastable melting, the origin of this metastable melting, and their implications in like mainly in phase transitions, and then we can always discuss beyond that. And this is really up to discussions. I haven't put much thoughts on that how this can actually influence our understanding for the Earth systems and others, but we can always discuss because phase transition is so common and should definitely influence our understandings of many systems. So first terms. So here I put here is basically the Tm is the melting of a stable solid. So when a stable solid is heated, and of course it melts. And then when a glass material, for example, is heated, there's a so-called glass transition. And that glass transition, it's also experimentally determined. We call it Tg. And what I mean by metastable melting is actually between this Tm and Tg if we plot that along temperature. And then below the glass transition, let's call it vitrification or amorphization. So just for now, because sometimes it's interchangeably used. But let's just call that. So just for the sake of discussion, this is between this. And then above this Tm, of course, we call it melting. As I said, this is not new because by supercooling, we know that there's a lot of materials that display supercooled effect. So we can definitely reach to metastable melting. It's not new. And we can also heat a metastable phase like glass to pass the glass transition and get to the liquid. So we get metastable melting. So it's not new. So the question is really that, let's say, if we have when we add pressure, then we have, let's say, a melting curve like this for solid 1 and a melting curve like this for solid 2. This is the extension of these melting curves. And let's assume that there's a glass transition temperature like that. And then for amorphization below glass transition temperature, it's actually being well studied. One example, of course, the famous example is H₂O. And H₂O, we know that has a negative melting curve. And then at temperature very low, of course, the H₂O displays so-called ice 1H phase. And as Mishima et al. Actually in 1980s and 1990s, they actually compressed this ice 1H at low temperature. And then at around between half GPa and 1 GPa, almost the extension of the melting curve, they actually observed so-called high-density amorphous phase. The ice 1H amorphized. We can call this metastable melting, but as I say that, I would prefer this amorphization because this is definitely below the glass transition. Another example is actually SiO2, that as we compress quartz or coesite to over 20, 30 GPa, we also see people, it also has been observed that the SiO2 get amorphized. And that is also interpreted by the extended melting curve of both quartz and coesite. So this is like pressure-induced amorphization is actually, something has been observed extensively actually in many materials. What about decompression then? There's actually a lot of examples about decompression-induced amorphization. Calcium perovskite, or I should probably call bridgemanite, maybe perovskite is better here. So this calcium perovskite actually, upon pressure release, it becomes amorphous. So we can view that as a decompression-induced amorphization. So that's one example. And for silicon, for example, if we increase pressure to silicon and then fast release the pressure and we actually got amorphous. Of course, this is like decompression rate dependent. If we release slowly, we get some kinds of metastable crystalline phases. If we decompress fast, we actually get amorphous silica. So that's also an example of decompression-induced amorphization. And the other examples actually is not directly by pressure, but it's related. Like for MgSiO3 bridgemanite, this is already, it's a pressure recovered sample, and at ambient pressure, if we heat this sample to 400 or 700 to 750 Kelvin temperature range, and we see vitrification or amorphization of this bridgemanite. So that's kind of indicative of, this is a metastable phase, and it vitrified. Similarly, if we apply this heating to stishovite or coesite, they also actually vitrified at 550 and 1100 Celsius, respectively. These temperatures are all below the glass transition of SiO2. So we see actually a number of examples as well for decompression-induced amorphization. So below glass transition, we have observed a lot, and we have a lot of examples related to that. The real question is that if we really increase temperature and like between real melting and glass transition, what would we see? And of course, as I mentioned that we can actually supercool a liquid down. We can see metastable liquid. We can use temperature like heating up. We should be able to see metastable liquid. That's there. But here, today, what I would like to discuss is basically when we apply pressure, decompression and compression, what we would see. One example is actually bismuth. We did that. And this is actually an interesting metal. It's a kind of semi-metal. It's actually play an important role in condensed matter. It's the first metal, the Fermi surface was determined. And also the first metal with large magnetoresistance. Bismuth actually has a very small Fermi surface with Fermi wavelength of like 30 nanometers. It's a huge wavelength for bismuth. There's new effects like electron fractionization, quantum spin Hall effect. It's a very active, it's a subject in condensed matter. It's well studied. The bismuth actually, like the bismuth what we have for bismuth 1, it actually has an open structure. It's a rhombohedral structure with layered structure. Rather, structure is relatively open. And then as we increase pressure, it's more compact. It's about like a 5% volume clamp. But still, it's a layered structure for bismuth 2. And then for bismuth 3, it's a guest host type of structure, incommensurate structure, complicated, very dense. And bismuth 4 is actually OC60, is also compact and dense and complicated structure. So it's from the structure point of view, it's also quite an interesting system. Pressure is relatively low. So it's experimentally, it's very easy to handle. So we did that. We just use diamond anvil cell, externally heated diamond anvil cell in neon medium. So we provide a hydrostatic pressure. And then we basically monitor the structure of bismuth with synchrotron X-rays. And this, as we heat to that temperature, and then start from 1, 2, and 4, as expected, as we increase pressure. And we keep the same temperature, and then we decompress from bismuth 4 or bismuth 3. And then here, when we reached in this PT condition, we clearly see, let's call it non-crystalline, because from X-ray we cannot really distinguish whether it's glass or liquid. I put this liquid because we have later evidence. So it's a non-crystalline bismuth. And then eventually, as we decrease pressure more, we see bismuth 1 phase. So this is rather surprising because external heating, it's very easy to keep temperature stable. And then we basically just increase or decrease the pressure. And then we see, it's actually repeatable. If we, at that point, we increase, it will go this one, and then we decrease pressure, we still see liquid. So at one particular PT condition, we see actually 2 distinctive states. That's actually, that is actually when that I kind of like, oh, this is probably, something is metastable, whether it's from liquid or from crystalline. So we actually did experiment, just map the experimental conditions in that PT area, and then did a series of experiments. And consistently, as we decrease pressure, we actually observe the liquid phase, non-crystalline phase there. And interestingly, that when we actually tap the system, or we increase temperature at one, let's say, for example, this one, we decompress, and then we stop here, and then we decrease temperature, and then the non-crystalline stays, and then eventually it crystallizes. The open symbol represents the crystalline phases. And then the same here is that we decompression, and then we reduce temperature, and then we increase temperature. Oh, no, I'm sorry, this one is actually, this one we decompress, we increase temperature, and then it also crystallizes. So as we perturb the system, it actually trigger the crystallization. Then we actually, this is, I have to use this. This is actually like during the compression period. So as we go, we just, this is just an optical image. So this is kind of like a pathway that, a compression pathway, that as we increase pressure, the system looks like, the morphology of this sample. It's sharp. It looks like it's a solid at least. It's not morphology of liquid. But as we keep that, and then as we decompress, and then the edge becomes like round and displaying some kind, the morphology seems to be related to liquid. So we kind of convinced that the non-crystalline pattern we observed from X-ray diffraction is really the liquid. But that is below the melting, as also indicated, as we increase pressure, we do see the solid-solid transition. But that happens only when we decompress some pressure. So we also, blue symbols here is actually the cooling path. So we actually increase temperature very high, make sure that it is thermodynamically molten state bismuth. And as we cool down, we actually clearly see the supercooling effect for bismuth, and then until to this temperature that it crystallizes. And we actually did the 2 pathways, like also here, as we cool down, and we do see the supercooling effect. So that means that in this temperature range, the bismuth can appear as a supercooled state. And that's actually when we thought that, okay, well, why not that bismuth probably becomes metastable, and we kind of like, that metastable state, metastable liquid state, is preserved as a kind of like a supercooled state. So that's our interpretation for bismuth. So just a brief summary for this bismuth sample. We found that a crystalline bismuth phase melts directly into a metastable liquid. This metastable liquid can be maintained for hours. We can actually maintain for until the external perturbation are applied. So that's what we observed for bismuth. The second example is actually H₂O. H₂O is, of course, it's a very common liquid. But it is actually a very weird liquid with displaying a number of anomalous properties. A few examples like this is density, compressibility, and heat capacity. This is actually the temperature range like close to our room temperature. We know that water display density maximum around 4 Celsius or 277 Kelvin. And then for compressibility, actually it displays a minimum around like 319 Kelvin, or heat capacity also display a minimum at that. And for normal liquid, this is kind of like a dashed line here. It usually like goes, changes as a function of temperature. But water clearly show not a normal liquid. Heat capacity, of course, is related to density. Heat capacity is related to entropy, and compressibility is related to density. So one is density, one is entropy, and they all display anomalous behavior. And it's widely accepted that water is abnormal, and it cannot be simply explained by thermal fluctuations and so on. It's a very unusual liquid. When actually we cool further down to a supercooled region, it's being even more, the anomal behavior is even more profound. Like there's a number of properties like liquid density, diffusivity, viscosity, and others. They all actually seem to point to one point. If you plot against this, and then people actually propose that there could be singularities at around like 228 or 220 Kelvin range. So it is kind of like a very unusual liquid. This is actually the put together, it's kind of like a metastable phase diagram. This term may be not accurate enough, but anyway, just to put the PT ranges for all these metastable phases together. LDA stands for low density amorphous. HDA stands for high density amorphous. This is crystalline phase 8. And then this is actually the supercooled region. And then up there is the normal water there. The melting line is not there. And then based on this LDA, based on actually the pressure-induced amorphization and the appearance of LDA and the PT range, theoretically, actually, it's being proposed that there could be a phase line between low-density liquid and high-density liquid. Low-density liquid this side, high-density liquid this side, and then there's a second critical point between these two liquids, and then above that is basically a fluctuation between low-density liquid and high-density liquid, the widow line. The extension of this point is actually somewhere close to the singularity point that I just mentioned, like close to like 220 to 230 Kelvin range. And then, of course, that if that theory is true, then we can explain a lot of anomalous behavior of water, including the supercooled water and the water above that. So in other words, that the water that we drink now is actually not a normal liquid. It's actually could be just a mixture of low density liquid and high density liquid, and that's that is also quite significant from a life point of view, because above like a certain temperature, like 48, 50 Celsius, the water becomes more normal. But this is when water becomes normal. This is actually the range that is actually very difficult for life to sustain. The life is actually usually below that temperature. So this is something that is, I think, has some fundamental significance there. But back to this H₂O itself, there's actually so-called no man's land. Why do you call this no man's land? Because in this white region, it is very difficult to actually obtain amorphous or liquid state of H₂O in this PT range. If we cool down from top, basically there's a homogeneous nucleation happens. And the crystal grows very fast. So no matter how fast we cool down, we can probably extend a little bit, but eventually it will crystallize. And similarly, if we warm up from glass, we may see a signature of the liquid appearance, but immediately it will crystallize into ice. So in this range, what we see is only crystalline ice, but not the amorphous part or liquid part of H₂O. And that's actually, people call this is so-called no man's land, meaning that experimentally we cannot reach there. So this is actually the important question, of course, that whether we can really see the low density liquid for H₂O there. And the approach we do is to use pressure. We use kind of like a developed so-called double diaphragm control, meaning that we actually use a membrane type or diaphragm type of pressure control device so that we can release or increase pressure very fast. And this actually is compatible to put the cell into cryostat so that we can cool down and reach to this temperature. And we also have developed so-called piezoelectric control device. And this is also compatible with cryostat so that the pressure, the compression or decompression rate can be even faster at controlled temperature regions. So we use this technique and then apply, and then put this, integrate this with synchrotron radiation to monitor by X-ray diffraction. And then we apply decompression from crystalline ice 8 phase, and then try to reach to this no man's land and see what we can observe. And the temperature range we cover is from above the glass transition to about 170 Kelvin in this range. So this is what we have observed. If we apply kind of like a slow decompression, so this is actually ice 8, and as we slowly decompress that, we actually observed like ice 6. This is kind of like a metastable crystalline phase. So it's not liquid. And then eventually we see ice 2, and then later on we see ice 1 growth as it should be, because ice 1 is the stable phase in that PT range. When we apply the decompression rate very fast, and then we start with ice 8, and then suddenly this is actually a very fast decompression here. This is actually already at ambient pressure, or even, in fact, it's in vacuum because of cryostat. And then what we see is actually the non-crystalline ice clearly appeared. And actually, the duration, the appearance actually lasts for several seconds, enough time for us to collect the liquid structure data. And then eventually, it's actually after a few seconds, it actually, ice 1 grows from that, let's call it non-crystalline ice at this point. This is actually kind of like the decompression rate. So this is going higher. This is the temperature range. So at the relatively low temperatures, we don't need to have very high decompression rate. We can actually easily observe this kind of non-crystalline ice. As the temperature going higher and higher, we need much faster decompression rate in order to catch this non-crystalline ice. This is actually the measured liquid structures, not liquid, non-crystalline structures of ice. So we see this, and then this is ice 8, and then non-crystalline ice, and then ice 1 grows. And then sometimes I use liquid, sometimes I use non-crystalline ice, because what we can really tell is actually non-crystalline. Whether this is liquid, it's actually being a question that we have been asking. And one thing that we can actually measure is actually the growth rate of ice 1. So as we actually measure the growth rate of ice 1 at different temperatures, we can actually fit this to Avrami equation, like a typical Avrami equation. Actually, the fits are reasonable. And then, of course, from this fitting, we get characterization time, and so-called N is the Avrami index number. This index number is actually well documented that this is if this N is integer, the growth mechanism is more interface controlled mechanism. And if that is half integer, it is more diffusion controlled growth. And as we can see that the N number that we obtained from all these temperatures are more or less close to this half integer. So this actually gives us some kind of indication that this non-crystalline phase may be indeed a metastable liquid. Another thing is actually we plot this characterization temperature against temperature. This is actually will provide us a test that whether these growths follow the Arrhenius behavior or not. And clearly, we see that there's a kink as the temperature is increased, and somewhere around here. And this kink is actually an indication of the change in relaxation mechanism. And what we interpret is that here at relatively lower temperatures, it's kind of like a strong liquid with or viscous. It's and then at higher temperatures, it's more like a fragile liquid. Or this kink may be a decoupling from the self-diffusion from the whole structure relaxation. So this is something that is actually on the right side here. This kind of behavior is actually well documented in metallic glasses, and as they change temperature, there's often display this kind of phenomena. And this is basically we kind of like use their interpretation for in this case as well. So, but regardless of the mechanism of this kink, it's clearly indicative of a liquid, not like a glass state. So that's why that we call this is a low density liquid. Actually, I'm going to talk about why we call this low density, but we can call this as a metastable liquid. Here is kind of like a viscous or strong liquid. And then below this line, which is the glass transition. We plotted this against the glass transition temperature. That is, of course, is the low density amorphous below the glass transition. So then why do we call this is low density liquid? This is, of course, the information is from structure. This is the next subject that we actually, because we can measure the structure, so we actually can address this question. This is actually the plot from a recent publication by Selberg. They actually measure the supercooled liquid, from the normal liquid all the way down to the supercooled liquid. This is a structure factor of the first two peaks, S1 and S2. And the interesting part is that you can clearly see the change, the separation of these two peaks as a function of temperature. And then they actually, this is by simulation, they actually this is actually G2 stands for the oxygen-oxygen impaired distribution function, the oxygen-oxygen distance. And the intensity of G2, the oxygen-oxygen, is highly correlated with the separation of these two peaks. In other words, that this separation of these two peaks indicates the degree of tetrahedral configuration, because oxygen-oxygen distance gives you an idea of the tetrahedral configuration of the liquid or gases. So that's what they are based on. And then they can plot this the degree of tetrahedral configuration as a function of temperature. So we actually put all this together with our data. These open symbols are from their data, together with some of the data from Skinner et al. At the relatively high temperatures in supercooled region and in the normal liquid region. So the supercooled and the liquid is actually relatively continuous in terms of the delta Q is basically the separation between the first and the second two peaks. That is actually indicative of degree of tetrahedral configuration. It shows actually strong temperature dependence for H₂O. Plotted here is actually the position of the first peak. It also shows like a strong temperature dependence for the first peak. The solid symbols here and there, this is actually the separation part, actually is from our measurement. We have also some data for low density amorphous that is actually below like 130 Kelvin. And these are the data actually from so-called low density liquid. We call it low density liquid. It's the metastable liquid that I just described. And our data show a very weak temperature dependence. So it's almost like no change there. So I mean, of course, dashed line is kind of a wild extrapolation. There's no theoretical base on that. It's just for ice. And then we indeed see that we kind of like, if we really extrapolate, that this crossing point is somewhere around 220. In fact, that is very close to the extended Widom line. So whether this is can be all connected or not, it actually is a subject of further studies. But what we show here is clear that for the liquid phase that we observe, at least it's actually the tetrahedral configuration has been fully developed. It's not in that region anymore. It's actually fully developed tetrahedral region. So that's why that the metastable liquid for H₂O we observe, we call that it's a low density liquid with tetrahedral configuration fully developed. So this is the kind of summary for H₂O part. by fast releasing pressure, ice 8 phase melts into a metastable liquid in no man's land in this temperature range. The metastable water is a low density liquid with tetrahedral structure fully developed. And this experimental evidence strongly supports the two liquid model, because two liquid model, we have to have a low density liquid, while the normal liquid is more in the high density liquid side. So far there's a lack of experimental evidence for low density liquids. And with this metastable kind of decompression approach, we actually observe that there is a metastable low density liquid there. So that's the contribution, I think, from this part. So back to this diagram. So we have evidence of metastable melting upon decompression. We have the example from bismuth. We have example from H₂O. And of course, there's a number of examples from literature about amorphization and vitrification. And then the question remains, is during the compression, actually we have applied compression, try to see the metastable liquid. No matter how fast we do, we actually haven't found so far. It may be not, at least for bismuth and H₂O, we haven't observed any. Whether it's there, and why it is so hard to observe a metastable in the compression path, I still don't know. And there must be some reason behind that. But this is still a question mark. We don't know. So I tried to spend like just the next few minutes to kind of like discuss that, my understanding of the origin of this metastable melting. And from thermodynamically, let's say this is the stable solid, this is the liquid, and then we have a metastable solids or gases like up there from the energy temperature point of view. And then, of course, this is melting for stable solid. And then for metastable phases, when it crosses the liquid, it will appear at lower temperatures. So the metastable phases always melt at temperatures below melting temperature. So that is, it's like a typical case is for glass. Glass as a metastable solid, the glass transition is always below the melting temperature. So that thermodynamically, of course, it is reasonable. So, and also that's a support that the metastable melting can appear actually wildly if metastable solids are involved. One example actually from literature, it's rather recent, last year. It's actually for a metallic glass. Well, metallic glass actually show that from a metastable phase, solid phase, and then to a liquid, and then to a stable solid phase transitions. So the evidence actually is from the calorimetric data. And this is actually, the data here is actually at a different heating rate. And when they have like 60 kelvin per second, first they see the glass transition, and then they see the first crystalline phase, and then the second crystalline phase, which is the stable phase, and then eventually they see the melting. So that's what they see. But as they go very fast, so the T1 becomes this one. This is the T1. T1 is a metastable solid. And then after that, they actually see this so-called TE, and they interpret that as the melting of T1, and then immediately followed by T2 phase, and then eventually reach to the melting of the stable solid. So what they claim is basically that from the glass transition liquid, T1 phase, and then in the middle here, they actually see the liquid phase. So it's kind of like the solid-solid transition mediated by a liquid phase. So that is I think that it's a quite interesting observation that the liquid can appear between two solids during the phase transition. So if we look at the thermodynamic basis from pressure plot, then this is a liquid, this is solid 1, and this is solid 2. That is kind of like similar to the phase diagram that I put it there. And then, of course, that this is so-called the pressure. This is kind of like a melting point, while that is actually the stable phase is here. So if we have one path that is, let's say, decompression path from a stable solid 2, and then kinetically, if the solid 2 to solid 1 is kinetically hindered and passing across this, then you will reach melting here. And then the liquid may stay for a while, and then, of course, eventually will transform to solid 1 phase. And then similarly, if we do compression, and if we kind of like, if this transition is kinetically hindered, then you may get the liquid state there, and then eventually to S2 phase. So thermodynamically, I think the existence of metastable melting is actually can be really understood by this kinetics argument. And then on the other hand, that this is a important implication of this is that intermediate liquid may occur in solid-solid phase transitions. So that is kind of like an implication of that. So back to this bismuth, we have, I explained this kind of like experimental efforts that we have done in that PT range. So on the right side, we plotted the probability of nucleation for different phases. Plotted against this transition stands for pressure transition stands for like phase 3, phase 4 phase. The pressure for transition from phase 3 to 2 phase, let's say, and then the difference is plotted against that pressure. So this actually towards right, that means that the pressure gap is getting bigger and bigger. And then this probability, of course, is related. There's a kinetic energy there. And this kinetic energy is actually related to gamma is the interfacial energy. And delta GV stands for energy difference between two phases. Energy difference between two phases. So this is kind of like our schematic understanding that for the bismuth, for this decompression-induced liquid, DIL, to occur, meaning that that here this delta G has to be small, and this small delta G is actually mainly contributed from the very small interface energy. So between kind of like the appearance of liquid reduces the interface energy a lot, and that actually contributes to this small delta G. And then it causes the more probability for nucleation of this liquid phase. Then why this liquid is preserved in this range, this is actually more related to this delta GV, because for bismuth it's quite unusual that there's almost like a flat melting curve involved. So in other words, that there's no density difference between liquid and crystalline solid underneath that. And the delta G between liquid and crystalline solid 2 is actually very small. And then because this is so small, and that causes this actually delta G relatively big, that hinders the nucleation of phase 2. That's probably the reason that we see that the decompression-induced liquid for bismuth, for hours in our experiment. Of course, then eventually, when it reaches to phase 1, this delta G becomes bigger, and then the phase 1 grows later on. So that is our current understanding for bismuth. And then for water, of course, it's for H2O, the energy difference between ice 1 and the liquid is probably not too small. That's why that it is basically very time dependent. When it's slow, we see crystalline phases, and we really need to go very fast in order to observe the metastable liquid. So I just very quickly just to have some kind of implications of these observations. The main point is really just between two solid-solid transitions. That transition can be mediated by a liquid. So in other words, that a metastable liquid may appear in solid-solid transitions. This is if it's displacive, I would say probably not. It's the transition probably will go from one crystalline to the other. But that may happen quite widely, I would say, in reconstructive phase transitions, and that may be mediated by metastable liquid. This is actually also supported by a recent publication in Nature Materials that they actually observed like a so-called two-step nucleation mechanism in solid-solid phase transitions. This is actually an experiment based on colloidal system. So this small ball is kind of like a few hundred nanometers, and with this high magnification microscope, they can actually see these balls, to see this ball changes. And they actually deposit this colloidal system on the surface of some substrate, and then they change the temperature. So the tension and the temperature both changes, and that pretty much change their colloidal kind of interactions, and then the material actually will undergo phase transition. So the square is actually the initial state, that's the green side, and then the triangle is actually the product state, it's the final state, and they can actually just use the microscope to watch how from one state, initial state, to the final state, how the process goes. And the marked red area is actually the liquid state that they observed. So they call that the nucleation is actually 2 steps. One is actually the breakdown of this square, and the system becomes a metastable liquid. And then the final state actually grows from that liquid state. So this is, I would say it's pretty much the same concept that I have been describing for bismuth and H2O. So finally, I just put the summary here. The metastable melting has been observed for bismuth and H2O under decompression. Pressure-induced metastable melting may be more common than we thought when pressure is applied. And the implication for this is actually the solid-solid phase transition may be mediated by a liquid. And that, I think, that's what I mean, that if we apply this concept to our systems, Earth systems, planetary systems, I think the implication can be huge. And that is actually really, I will be very happy to discuss with you and see what kind of areas that we can look into that. Thank you for your attention.
Very interesting observation. Any questions? I'm going to start So this liquid observation is really very interesting. In the end, you talk about the nucleations. So one of the experiment you could do is in the bismuth, plant another high melting temperature metal. So it's serving as a nucleation. So you actually, if your observation, I'm sure is correct, but you will also see the decompression will nucleate on this. So in that case, you will eliminate metastable liquid. So that's a possible experiment.
Yes, that's in fact that for bismuth, the so-called decompression-induced melting happened only when we use helium medium. So in other words, that the metastable liquid can be sustained only under a very good hydrostatic medium. If we use solid medium, for example, which means that we have some stress, even a little bit of stress, at the, if we repeat the experiment at the same temperature, compression and decompression, we just see solid-solid transitions. Because the supercooled liquid can maintain only under a very good unperturbed hydrostatic condition.
That's because you don't have a nucleation.
Yeah, that's right. So that's the same same thing that you're talking about. Yeah.
Did the time scales of nucleation for water that you find, do they match up with what they found at LCLS? I think those were at
From cooling down, right?
from cooling down to like 230 Kelvin.
It does not match at all because because cooling down, they are competing for the nucleation from at higher temperatures, right? So cooling down is at the high temperature side, and what we do, decompression, is actually at a much lower temperatures. So we are really talking about different thermal energy involved, and they need to actually cool down at much faster speed in order to catch basically the liquid water before it nucleates. So very different time frame. We can actually manage to measure the liquid at the millisecond level, but they need to actually microsecond, nanosecond level. So it's a very different time scale.
So metastable liquid and similar to supercooled liquid, right? That you said.
I think it's similar, yes.
So why you use the new name for metastable liquid? Because supercooled liquid is widely used, and the last thing is isn't that like a new word might confuse lots of secrets?
That's certainly a very good question. The reason I think it's a metastable liquid I use is basically towards the end I mentioned about one implication is that it's basically when we deal with solid-solid transitions, that may be mediated by a liquid. And that liquid, if we say that liquid is a supercooled liquid, it probably is more confusing. So to say that is a metastable liquid is probably more acceptable. So that's the main reason behind that.
So I have a technical question. So when you look at the water liquid decompression, you have a broad peak, right? And in the decompression.
Right.
So how broad? What is there a quantitative difference between the supercooled liquid and the water and your liquid in terms of broadness of this peak? And certainly it's going to reflect in the structure of the broadness of that.
The peak broadness, right?
Yeah.
Actually, I haven't made that careful comparison yet. So the broadness of the peak, I would say it's very similar. It's mainly like the peak separation.
But the actual broadness of the liquid is similar to what you're seeing in the. This is a process data.
No, they actually did. They actually didn't report the raw data, so I actually cannot do that. But here that the first peak and second peak are well separated, and we are also well separated. So that's what we can say at this point. Yeah. Well,
So I have two questions. So first, all the examples you showed were one component systems. So what about in a
I think the phenomena probably will be more profound in multi-component systems. That can, because the fact that this can appear in single component system, it has to appear actually in more in multi-component systems.
Okay, so
That's my expect.
are you looking for that?
It's a good, of course, it's a good direction, but not immediate plan. But it's something that we should.
Okay, the other question is, I mean, if you're dealing with the metastable extension of the melting line, can you actually map out where that line is? I mean, so normally people map out stable phase lines, but can you map out exactly where the metastable extension goes, or is it really driven by kinetics?
The experimental mapping is possible because we can always note down the first appearance of amorphous phase or liquid phase. In fact, that for bismuth, for example, we actually did draw like a line. This dashed line is actually our so-called mapped line for this metastable melting, because somehow that, as we decompress, and then the first appearance of the crystalline phase actually more or less follow this line.
Makes my point, because I mean the metastable extension has to be continuous with the stable part. What line is that you're drawing? I mean,
You expect to see this line, right?
well, that would be for 4 going to.
That's right. This is for, but what we observe is actually a little bit like, there's an over decompressurization effect. That's if I may, I can change to this.
Okay, actually.
Here it is, yeah. So if you, for example, so you need to kind of like, if the kinetically is hindered, so there's an extension there, and then to the liquid.
Yeah, I would rather go back to where you just were.
Okay.
So,
Yes.
yeah, so here, so there ought to be some kind of metastable phase diagram for 3, for example.
Mm-hmm.
So 3 going to 4 would continue to the left if you didn't make 2, for example. So do you also see that? That would be a metastable solid. So I guess you do, because you see the triangles going to the left there.
Yeah.
Left of the vertical line between 2 and 3. So I mean, what I'm saying is you could kind of map out the metastable phase diagram.
It is possible, yeah. What I'm saying is that it is experimentally possible that we can map all this out. Similarly, actually for H₂O, I did show that the metastable phase diagram for H₂O. That's, of course, accumulated from the literature data.
Yeah, I think if you fit like a I'll stop talking. If you fit like a thermodynamic model to all of your data, you might be able to know where the rest of the lines go.
In general, I would think map of the not stable phase diagram is going to be much more challenging experimentally, because as we showed, nucleations as well as
Right.
stress environment is going to affect all pathways.
Right.
All going to affect. That's why we use equilibrium phase diagram. Always
Right.
know exactly where the transitions are. Anyway, this is a very interesting discussion. And Guoyin is going to be here this afternoon. We'll have lunch next door, so if you want to join us, feel free. And thank you again.
Thank you.
it was very. Actually, I hear this is the second time